Well, we now come to kinematical equations, and these equations should be proved graphically. So when we prove them graphically, we need to draw the graph for the, it's very important that the graph should be drawn for velocity time. And as we draw it for velocity time like this, we have this as velocity, and this is time. And then this is the initial velocity, what we have as u, and this is the final velocity, what we have as v. And now if I drop a perpendicular from here, and if I join this line like that, and if I take this to the ground, then this is from 0 to t, which is the time axis. And now the slope, as you know, the velocity time graph slope is acceleration, so it is tan theta. Now this eventually becomes v minus u. I hope all of you understand it, as this is v and this is u, so this should be v minus u. So acceleration comes to be v minus u by t, and from there we go on to write that v is equal to u plus at. So that is your first equation that we have, v is equal to u plus at. Now we'll go on to the second equation. Now the second equation for the same graph, if I draw the graph right again, it's velocity versus time, and this was the graph where this was u and this was t, this is 90 degree, and this was v minus u. So now the next that I do is, I know that the area of the velocity time graph is distance traveled. So if I go on to calculate the distance, I should take the total area under this curve. So the area constitutes of this rectangle, which you can understand is u into t, so that is ut, and this area, which is half into base. Now the base, as you can see, t, and the altitude. So the altitude is v minus u, which is equal to at, as we have already learned. So this should be equal into at. I'll repeat that the area of this total graph is what is the distance traveled. Why? Because we know that the area under the velocity time graph is the distance traveled, which we write like this. Now here we calculate this area. We take the area of this rectangle, and then we take the area of this triangle. And this area of the triangle, you can see half base means t, and the altitude, which is v minus u. In the previous page, we have proved that v minus u is nothing but a into t. So that makes it at. So that there you get the second equation, which is ut plus half at squared. Now we come on to the third kinematical equation. Now for the third kinematical equation. For the third kinematical equation, we draw the graph again, as it's very important to have the graph in front of us time and again. So we can see that this is the v minus u portion, and then this is the t portion, and this is the u portion, and this was theta. Now if I consider the graph as a trapezium like this, then what I can write? Well, I can write it the distance as this arm is u, so it is u, and then I can write that this arm as it is v minus u by 2 into the height, which is equal to t. So if I calculate this, then what I have is 2s is v into t. So when I have 2s is v into t, I can go on to calculate something else. So let's see now what we can do here. So let me again draw the graph like this, and I will do the calculation here. This is v minus u, and this is u. Now if I consider the areas we are talking about here, you can see this arm from here to here is nothing but v. So what we have, when we add these two, we have it as e plus v by 2 into this distance as the height as t. So what I have is v plus u is 2s by t, and previously I had v minus u as at. So now what I do is I multiply them. So when I multiply, what I have when I multiply v plus u is 2s by t, and v minus u is at. When I multiply, I have v square minus u square, which is equal to 2, which is equal to 2as. So that makes me v equal to u square plus 2as. So that is the third kinematical equation that I am having. So this is how we operate the kinematical equations graphically. That's all. Thank you. For testing your understanding of this lesson and more videos, log on to www.tubelessons.net.